This video is presented to you by Physics for Students. To know more, please visit us at physicsforstudents.com.
Welcome to this video on differential geometry. My name is Shaunak and I welcome you from Physics for Students. In this video, we are going to talk about manifold, the fundamental concept of differential geometry. Before we go ahead, I would like to tell you that I'm going to make a series of this fundamental concept of differential geometry. This is the first video on the fundamental concept part, and here we will be dealing with manifold. I would like to tell you that this is going to be a fairly easy video where not much of complex mathematical equations are involved. I would try to give you a fairly easy way out in order to understand manifold, Riemannian manifold, Riemannian metric, and how the history of manifold unfolded with the passage of time. So this is very important because this is the first basic understanding, because on the basis of manifold we further a complex mathematical and fundamental concept of differential geometry evolves. So you can take it as a fairly easy video, a kind of a more or less intuitive approach in understanding manifold. So before we go ahead, let us understand what are the topics we are going to cover. The first would be we would just understand the basic idea of what is differential geometry. Then we will understand what is manifold and a very interesting history on how the concept of manifold evolved through the scientific progress of time. What is visualizing manifold, because we need to visualize, otherwise mathematical equations doesn't always help out. What are the different types of manifold, how we can understand and analyze manifold better. Tangent vector, tangent bundle, tangent space, these are important in order to understand Riemannian manifold. So you can tell these are the prerequisites. We also understand Riemannian metric, and lastly, why should we understand manifold? What are the usage and what is the reason of undergoing this study? So I think this is a good time to start ahead, and we have already laid down what the topics we are covering. First, we need to understand what is differential geometry. Okay, so first of all, let us understand that what is differential geometry. I'm just going to give you a kind of a basic idea what it is. So you can say that differential geometry is basically a study of shapes, spaces and objects, obviously in curved surfaces. And you can say it is a study of nature of curves in three-dimensional spaces. It uses calculus, linear algebra to study Riemannian surfaces, which is one of the topic of this video. A study invariant under a broad transformation. Now this is easy. If you have seen my earlier video on differential geometry, the basic idea is to create a kind of an invariant transformation, because in general relativity and other areas, once we change the coordinates and if the vectors and the measurement is invariant, it becomes much easy to compute the distance and other calculations. It is used in general relativity, obviously, global positioning satellite, 3D modeling, and thermodynamics. So this is more or less that what is differential geometry and how it is used. Okay, so this is just to give you a kind of an idea that these are the different shapes. So these are rounded, and this is the manifold, and you get a kind of a weird, all kind of shapes, hyperboloid, spheres, and cylinders. So you see this. So this is just, differential geometry actually deals with this kind of complex surfaces and shapes and norms, etc. So this is just to give you a kind of a visual idea that these are the things that differential geometry deals with. So what we can say in simple words is that it is a branch of mathematics that studies the geometry of curved surfaces and manifolds. So you see I have written manifold in red because this is the subject of our video. It uses ideas and techniques from differential calculus. We will soon see, because the word differential geometry means that we will be using differential calculus. Okay, a branch of geometry dealing with geometrical forms, mainly with curves and surfaces, by methods of mathematical analysis. So we use mathematical analysis for this. Lastly, in differential geometry, the properties of curves and surfaces are usually studied on a small scale. Now this is important to understand, because differential geometry, because we are doing differentiation, which is on a very infinitesimal arena, so it deals with on a small scale. So all the properties of curves etc., which differential geometry deals with, these are studied on a small scale. The question which immediately comes to your mind is that then what is done on a large scale? The answer is topology. So topology is a branch of mathematics which deals with similar kind of things, not similar, a little bit more, which is on a broader, on a global scale, and differential geometry studies things on a small scale. Okay, so first we start with what is a manifold and who discovered the manifold. So what we will do is that we start understanding the concept by tracing back its root. Here we will understand the concept of manifold first on an intuitive level, getting a broader idea, and then we will go into the mathematical intricacies. So we take those shapes which we have learned, and this is what which is called a manifold. So I'm just giving first of all a very basic understanding, a literary sense, what is manifold. So it deals with numerous different parts of elements and features consisting or operating of many of one kind combined, having many different features and forms, and a collection of points forming a certain kind of set, such as those of a topologically closed surface. So the fourth definition is a little bit kind of a mathematical one, or although it is not truly mathematical, but just to give you an idea. And it is whole composed of diverse elements. Even you can see it tells that to make several copies of, as with carbon paper. So manifold, as you can understand, it is comprising of elements which are combined, which has got diversities and several other things. So this is basically the understanding of the word manifold. Okay, so once we understand what is fold actually, when we start, there's a two words, many and fold. So what is a fold? So in general, fold means that we already know to bend it or cover or wrap up or furl. It is to bend or ply anything, to lay one over the other, and to clasp or enwrap closely, or to become doubled upon itself. So if you just look on the figure right on the top of your screen, you will see all those features are present in those objects. They are bent, they are wrapped up, they are, laying one part on the another, and they carry diversities, all those things. So just to give you a clarity on the area that what is many and what is fold. So all these shapes do have those features which we just read. Okay, so we see manifold comprises of two words, many plus fold. So the word many, actually it is coming from certain Old English Angelian. So it is called Monigfald, then the West Saxon Manifold, then the Middle English many and maniage, Proto-Germanic mangas, Middle Dutch, and then German. I won't dare to pronounce the German word, it would be erroneous. So, and the word fold is coming from Old English field, Northumbrian fald, and Proto-Germanic falda, and so on, Dutch woud and Gothic falp, etc. Just to give you an understanding that, what the words and how they came from in order to construct together to make the concept, make the word manifold. But these are not sufficient. We just saw the literary term, but who and how the word manifold got discovered. So yes, who discovered it? So first of all, what we need to understand is that the term was coined by the German mathematician Bernhardriemann. We all know who was Bernhardriemann. So one of the pioneer in terms of mathematics and different other areas of physics and mathematics around 1854. So it is this German word, I won't dare to pronounce, right? Which means manifold, and William Kingdon Clifford, who is known for Clifford algebra, translated it to manifoldness. Okay, so here is something which I would like to tell you, that in 1854, in his Göttingen, Riemann's Göttingen inaugural lecture, Riemann described a set of all possible values of a variable with certain constraints as this, the German word, because a variable can have multiple values, right? So he distinguishes between continuous manifoldness and discontinuous manifoldness depending on whether the value changes continuously or not. As continuous examples, Riemann refers to not only colors and the locations of objects in space, but also possible shapes of spatial figure. So you see, I have written here that continuous manifoldness and discontinuous manifoldness depending on whether the value changes continuously or not. So this is how the foundation of manifold has been laid. Okay, so right on the left hand side of your screen is the famous, I would say, Riemann's dissertation on the hypotheses which lie at the basis of geometry. So it was this historical book where Riemann first introduced the concept of manifold. So here it is. William Clifford, I just underlined in red, translated this to English. The basic concepts and ideas as well as their mathematical background are provided here in this book, putting Riemann's reasoning into the more general and systematic perspective which is achieved by later mathematicians like Helmholtz, Ricci, Weyl, Einstein, and the basis of his seminal ideas. Okay, so when Riemann presented his idea, okay, let me show you, right? So this is actually the English translation, right? So when Riemann presented his idea on a geometry in manifolds, I mean to say for the first time, you understand, in Göttingen, when people are not aware about this, he was completely aware that he was in a border region between mathematics, physics, and philosophy. Not only in the sense of pragmatic reason that his audience was mixed, but by the very nature of exposition. And during that time, there was no linguistic or symbolical frame inside mathematics which he would refer to, even only to formulate the general concept, right? Okay, so it was during this time what I would like to take that basic to such a construction was, so Riemann explained to his audience the presupposition of any general concept, okay, which allows in a logical sense precise individual determinations. From the extensional point of view, such concept would form a manifold, and the individual modes of determination were to be considered, as Riemann explicitly stated, as the elements or the points of the manifold with either discrete or continuous transition from one point to another. Just note that right at the bottom, I have underlined this continuous or discrete manifoldness. So this is what was Riemann. Riemann scratched the draft for a conceptual starting point for what later was generally became known as set theory, discrete manifold, and topology, continuous manifold. So discrete manifolds and topology, continuous manifold, the basic foundation was laid by this paper, Bernhardriemann, in his opening lecture in Göttingen. So further what we see is that these concepts, it really takes time to gain mathematical value only if a sufficiently rich structure of functions on the manifold is available. Right, so I have written that this gave birth to the concept of manifold. Right, so a change of coordinates would lead to locally invertible differentiable real functions. See, this is important. So the paper that he read across in front of the Göttingen people, a change of coordinates would lead to locally invertible differentiable real functions. This was not made explicitly by him, but was to be understood from the context of the careful listeners or readers, right? So the distinction between local simplicity of manifolds because of the presupposition of local coordinate system and globally involved behavior was indicated by Riemann, but not particularly emphasized during the talk, although in other publications and manuscript it was slowly revealed. So here in front of your screen, what I just made certain important points that as you see that what I told, that invertible differentiable real functions is something which was not told by Riemann explicitly, but it was to be understood those who were careful listeners. And this is the basic foundation of general theory of relativity, which was laid down by Einstein. Because if you get really invertible differentiable real functions, then you can construct the theory of relativity pretty easily based on that. Okay, so once we understood that, what we now understand is that what is a manifold. So we can tell that a manifold can be thought of a smooth geometric figure of certain dimension. Okay, smooth, why I'm telling? Because it has got no kinks or self-crossing as such. So it may or may not be allowed to have context like a cube or a square, depending on whether it's a smooth manifold or just a kind of a topological manifold. So more precisely, every point on a manifold has a small area around it that looks locally Euclidean. Yeah, so this is very, very important. We are going to explore more on this. Every point on a manifold which is right at the bottom I have just shown you certain figures. Every point on a manifold has a small, very small area which looks locally like a Euclidean space. Okay, so once we have understood the basic, I'm going to say a very intuitive definition of what is a manifold, what comes next is that can we visualize the manifold, right? So let us see that what would be the visualization of a manifold. Okay, so what I would like to show you is this. So say for example, this is a kind of a globe, right? And this is one person standing. And this person actually starts moving around the globe. So he moves from here. I just mentioned those points and comes here. And from here, he further moves here and comes to this point. Again, he travels this direction and comes to this point. And he further moves in the opposite direction, comes to this point, and finally goes to this direction and comes to this point. Okay, so now this is something which the person is traveling over the globe. Okay, over a sphere or on the surface of the earth. So the movement as itself seems to be so. Now, finally he moves to here. So, right. So now what we do is that we try to trace the same movement along this kind of a pretty kind of, I won't say curved, but a kind of a flat surface. So I take the same person and he moves around here. I take the same person, he goes here, and then he goes here, and he then goes here, and he then goes here, and he goes here. Okay, right. So what I'm trying to show you is this. So when this person moving from a sphere is now being traced on a map which is flat, this is what is called a manifold. So anything which locally resembles Euclidean space near each point, right? So what I'm trying to tell you is that the traveling over the globe, if I am located somewhere out on the space, or we know that the earth is globe, but for that person, as that person travels on a flat space, right, that flat space resembles typically of a Euclidean space. That means we have the real numbers and we do the distance calculation whatsoever. So this is actually the global aspect and this is actually the local aspect. So this is basically we started visualizing what is a manifold. So understand that the concept of manifold is very central in many parts of geometry and modern mathematical physics because it allows complicated structure to be described in terms of well understood topological properties of simpler spaces. Let us ignore the term topological properties. Just wanted to tell you in that way. So as it turns out, like if you keep walking in one direction, eventually you would end back where you started, right? But the thing is that if you hold it up here, right, and you start to wonder whether the earth might actually be flat plane, given the right hand side, it is basically the flat surface, right? So wherever you go is that the surface of the earth is two-dimensional manifold or a surface. That means it is a space that looks locally like the Euclidean plane, but it might have different features being into a global structure. We are not worried about that. This is the type of visualization, a way to understand what is a manifold. Okay, so let us see what is the general definition of a manifold. So in general, see, I have put the topological word in braces because we won't consider what is a topological space, because again I have to go back and make things understand under certain sets and open sets. So let us consider a manifold is a space that is locally Euclidean. Okay, so loosely speaking, say for example, it just means that for every point in P, so for example, this is a point in P on an n-dimensional manifold. We're not considering n-dimensional manifold. Let us consider the sphere for this part. The points in the neighborhood, right, of point P, it can be x, y, z, whatever, can be specified by n coordinates x1, x2, x3 and so on. And there exists a continuous map from that neighborhood to Rn. So it is a locally Euclidean space. So here Euclidean or Cartesian space is a space of all real numbers which goes from x1, x2 and up to Rn. So a locally Euclidean space is a topological space that looks like more of an Rn. So what I'm trying to tell you is that Euclidean n space Sometimes it is also called a Cartesian space, or simply say, for example, N space is the space of all n tuples of real numbers starting from x1 ranging up to xn. Such n tuples are sometimes called points, although there are other nomenclature which is given. The totality of n spaces is denoted by Rn. So this is what I am trying to tell you more about manifold. So it is a space that is locally Euclidean, and locally Euclidean means it will have the real numbers, and we can further do whatever calculations that we do similar to a Euclidean space. So this is local and this is Euclidean. So just I wanted to make you understand. Okay, so let us take another example of the Earth, which is a two-dimensional manifold. So Earth is a two-manifold in R3. Why it is R3? It is in R3 because we live in a three-dimensional Euclidean space. So it is a two-manifold because every point of P, every point of P, we can specify P and other points in the neighborhood by 2 dimensions. So in general, any object that is nearly flat on small scales can be called as a manifold. This is again a very basic idea, a very basic understanding of what is a manifold. Just as I told at the beginning of the video that we are going to make a basic understanding, more or less of an intuitive. So any object which is flat and we have got points around the neighborhood, we can call it as a manifold. Okay, so what we do now is that we try to understand what are the different types of manifold which are there. So first we start with a one-dimensional manifold. So we get a long line which can be called, then we get a circle, then we get what is called a real projective line. Now in real projective line, we just give you an idea that is a real projective line is a projective line over the real numbers. It is actually, an extension of the usual concept of a line that has been historically introduced to solve a problem set by visual perspective. What is that? Two parallel lines do not intersect but seems to intersect at infinity. And we have got the real line, right? For the two-dimensional manifold, we have got a cylinder. We got the famous Kleinbottle, which was invented by Felix Klein in around 1882. We got a kleinbottle, and we have got a mobiusstrip and a sphere. Now just hold on. There is a very, very important and a very interesting history which I really found out through my study, and I'm going to give the credit to the researcher who have done that. Mobiusstrip, as whatever we see in Mobius, actually dates back quite old. So we go back to 200 to 200 and 250 CE. As you can see right in this figure, this is actually depicting Mobius strip, right? So you see that the zodiacal symbol are shown in the band that surrounds at the bottom. Okay, so this is, first of all, this is a central part of the large mosaic from Roman villa in Sentinum. This is the Aeon, the god of eternity, which is standing on inside the celestial sphere, and sitting in front of him is the mother of earth, goddess Tellus, with her 4 children, which is not shown here. I've just given the hyperlink from which I have taken this photograph. Now you see this one, the red circle, this is actually where Aeon is standing, right? So at the bottom, Aeon is standing with 1 foot on the internal part of the band. Now if this is followed clockwise, we arrive at the external part. You see this one. So here it goes and over here, right? So we arrive at the external part of the band over Aeon's head. Instead, if we go anti-clockwise, so let's go here and here. So which demonstrates the same position over his head, the internal part we see here, and which demonstrate the Mobius topology of the strip. Now it is worthy to note that the zodiacal symbol of the constellations are not all in their natural places in the band of the elliptic. It is at kind of a mix-up and error on that part. It might be a deliberate choice of the artist or whatsoever. But I would like to show you once more that this is actually, when we go this way, we reach up to the head of the figure, which is the inside, and then we come in this way and we come to the internal part of the band and we get the Mobius topology. So it is not something which Mobius discovered. It was quite some year back, right? Okay, further I would like to show you one book. This is Kitab Fi Marat Rifayat al-Hiyal al-Handasiya. This means the book of knowledge of ingenious mechanical device, and it was written quite early. Let me see. Yeah, so book of knowledge. It was by al-Jaziri around 1206. What I would like to show you is that you see in this figure there's a Mobius strip in the diagram of a chain pump, right? The chain pumps have been utilized for many civilizations. I mean to say Babylonian, Egyptian, Chinese, and perhaps the Romans used them during this Islamic golden age. So, however, this is the only case that it is found that in which the chain or rope linking the buckets for the pump is arranged in a Mobius strip. So you can see that these are the Mobius strip. It was translated and noted by Donald R. Hill, and it was originally written around 1206 by al-Jazari, and he is basically Jazari bit Ibn Umar, present day in Turkey. So this is a kind of a very interesting history, but definitely I have not done this research. So it is done by these people, great people, Mobius strips before Mobius. You can find it in arxiv.org, right? So yeah, that's it. So I've given the PDF file link also. You can just go and find it out. Okay, so we go ahead and understand what is a three-dimensional manifold. So we first get a kind of a three-sphere, and we get a solid torus. This is very interesting. Whitehead manifold. This was discovered actually by J.H.C. Whitehead while he was working on Poincare conjecture, and he found out that manifold, and he is considered to be the founder of homotopy theory. So we start with the four-dimensional manifold, which is even more interesting. This one is called the E8 manifold. Then we get Enrique surface. So Federico Enrique, now known principally as the first to give a classification of algebraic surfaces in birational geometry, is a very important person. And then what we get is Pascal del Pazzo surface. This was invented by Pascal del Pazzo, who was an Italian mathematician and is remembered for the first time describing this surface. What we get is also a complex projective plane and exotic R4. This was discovered by Michael Friedman, and in mathematics, exotic R4 is known to be a differentiable manifold that is homeomorphic but not diffeomorphic in the Euclidean space, and it was first found in 1982 by Michael Friedman. So this more or less completes our journey of what are the different types of manifold, and we now move to the most important and the central part of our video, which is analyzing a manifold. So when we talk about analyzing a manifold, what I want to tell you is that once we see the figure of a manifold, what are the further details that we can get? So here is a hyperboloid, a cylinder, and a sphere. So you see these are the, if we move around this way, what we get is a kind of a positive curvature because it converges at a certain point. These are more or less straight, so we can tell it has got a zero curvature. And this hyperboloid moving in this way has got what we call is a negative curvature. And what I would like to show you is that when we are talking about differential geometry, we take a kind of any kind of an arbitrary surface and we divide these surfaces into small parts. That means we are trying to see the differentiation. So we do a dy by dx or a dA, and what we can see is that we can apply the rules of the calculus now in manifold. So you see that on the left hand side, all these figures have got small boxes, right? Very, very small boxes. And these boxes are where our differential calculus is being used, and we can use the differential calculus. Now note here, it looks like an ordinary piece which is a Euclidean space. These yellow marks right at the left hand side bottom, right? These are all Euclidean spaces. What we can also tell is that given this kind of a figure and given this kind of a yellow box, which are these Euclidean spaces, if we map them, then what we get is Rn, where the real numbers varies from x1 to xn, and this is what we call that a manifold is a space which is locally isomorphic to a Cartesian space spanning up to Rn. So this again gives you a kind of a very basic intuitive visual understanding that if we divide them into small little parts, it gives rise, I would say it is locally isomorphic to a Cartesian space. Okay, so let us quickly look that once we have learned differentiating and then analyzing, getting the Cartesian pairs, local Euclidean, what are the benefits of learning manifold? What are the uses that we really understand? So these are the uses. You can just read through. It helps to analyze and study the curvature of surface. It helps to allow, because once we differentiate very complex forms, it becomes easy to understand. We can do calculus, we can solve complex topological problems, we can understand general relativity, which I have told you, and we will see in the Riemannian manifold how general relativity is extremely intricately related to Riemannian manifolds, and it helps us in computer graphics as well as perform CT scans. So just kind of an understanding that why we should use manifold and why we'll understand manifold, because this is important. Otherwise, we will lose interest in further studying. Right. So now we come to the most important part of our video in understanding what is a Riemannian manifold. Okay. So in general, what we call a Riemannian manifold, this is a very, very basic. Again, this is not a totally mathematical definition. But just to give you an idea, Riemannian manifold or Riemannian space is real, differentiable manifolds where each tangent space is equipped with an inner product, the Riemannian metric, that is defined as the shortest length, the geodesic, from one point to another along the curve. So in general, what we can say is that a Riemannian metric is a family of smoothly varying inner products on the tangent spaces of a smooth manifold. So Riemannian metrics, you understand, are very infinitesimal objects, but they can be used to measure distances on the manifold. It was first introduced by Riemann in his work, which I have shown you, in 1854. And during that time, the concept of manifold was extremely vague, and except for some known global example, most of the work of the geometers focused on local considerations. So the modern concept of Riemannian manifold really took a lot of time to unfold and understand. However, in this definition, we see 1, 2, 3, 4 important factors. One, what is real? Second, what do we mean by differentiable? What is a tangent space? And what is a Riemannian metric? Real, I think you can understand that it consists of what is called a real number. So I really don't need to understand. But differentiable, tangent space, and Riemannian metric, it is first we need to understand. Otherwise, we won't understand what is a Riemannian manifold. Okay, first let us understand what is a tangent vector. Now, in mathematics, a tangent vector is a vector that is tangent to a curved surface. Given this kind of a curved surface and this particular red dot, that's this red point, how are we going to calculate the curve? We are going to take the tangents, just like this. Given another, if this kind of a circle, we take this tangent vector, and further we take this kind of a tangent. So what I'm trying to tell you, that tangent vectors are described in the differential geometry curves in the context of curves in Rn. So because all these are curved, etc., so we need tangent vectors in order to calculate. And most importantly, general theory of relativity is full of curvature. So it first starts with a basic need. Yes, we need tangent vectors. Okay. The next important concept is that tangent bundle. Very simple. So let us consider tangent bundle is the collection of all tangent vectors along with the information of the point to which they are tangent. That means it is just a collection. For example, this being a manifold, some kind of a manifold, say for example M, and these are it is a differentiable manifold. What do I mean by differentiable manifold? I am coming next. Let us just understand this is a differentiable manifold, and these are all the tangent vectors which are going along the manifold. So it is just a bundle. That means we say a bundle of stick, so this is a kind of a bundle. It's a collection. It is where things are being collected of all tangent vectors. So these are further figures, and each of these figures you will see it is a bundle. It's a collection of all the tangent vectors. So we got the tangent vector, and now we assemble all these tangent vectors in a tangent bundle. Now comes something, as you can see, these are the small boxes, right? They represent local Euclidean spaces, and we got few points. What we can do, this arrow, this arrow, this arrow. Now we can actually perform differential calculus on them, right? So these boxes actually are locally Euclidean, and they are using differential calculus, right? So what we call, you understand that we were just using differentiable manifold. So a differential or a differentiable manifold is a topological manifold which has a differentiable structure. That means the structure, the basic idea of that manifold is something which can be differentiated using calculus. And differentiable structure comes from this one. A differentiable structure on a set M makes into an n-dimensional differentiable manifold on which you can do differential calculus. Right. So we started first with the tangent vector. The collection is called tangent bundle, and now these are the differentiable structure on which we actually calculate the manifolds calculation, and this is done through calculus. So differentiable manifold is something which has a differentiable structure, and differentiable structure is a set, say M, which is n-dimensional and on which we can do differential calculus. That is pretty simple and straightforward. Now let us understand what is a tangent space. Now in differential geometry, one can attach every single point, whatever be the point, say x, of a differential manifold, a tangent space. So intuitively, let us understand this one. You can see this is a tangent space. This is a sphere kind of a thing, and this is point x, which is I marked in red, and this just kisses through. Right? This point will just kiss through. So intuitively, it contains all the possible directions in which one can tangentially pass through x. So this is MTXM. I will show further figures. So the set of all tangent vectors. We have seen tangent vectors, tangent bundles. Now we are talking about tangent space. So all tangent vectors at a point form a tangent space T sub x of M. So let us see that. For example, this is a kind of these are the tangent vectors, this one and this one and this one. So as I told you that the elements, it intuitively contains all possible directions. So these are the three directions which goes in, and this is the bigger one, is the tangent space. Okay, so the elements of the tangent space are called the tangent vectors. The elements of tangent space, these arrows are called tangent vectors. So you can see it is a generalization of the notion of vector based at a given initial point in Euclidean space. So this is tangent space. Okay, now that we have understood tangent space, tangent vector, etc., the last thing which remains in order to understand Riemannian manifold is what is called a Riemannian metric. Now this is a pretty simple and a straightforward definition. A Riemannian metric is a family of smoothly varying inner products on the tangent spaces of a smooth manifold. Riemannian metrics are thus infinitesimal objects, but they can be used to measure distances on the manifold. So just hold on if you don't understand the internal meaning of inner products and tangent spaces. I will just explain you. So let us assume that M is a smooth manifold. A Riemannian metric G, so we denote it by small g on M, is a smooth family of inner products on that tangent spaces of M. What is an inner product? I will just show you. Just bear with me for a few minutes more. So this name G, which is this what we call Riemannian metric, actually associates each point of P in M. So each and every point, say P or X, this is a member of the tangent space of M. And this is positive definite because it is symmetric and in a bilinear form. So actually what happens is that a Riemannian metric makes it possible to define various geometric notions on a Riemannian manifold, such as angles, lengths, curves, areas, curvature, lot many, gradients of function, divergence, anything. Okay, so we further go into Riemannian metric and we understand actually the smoothness of this, I would say the G actually depends on this, right? So it must be smooth for every locally defined smooth vector fields x and y in M. So here it is, must be smooth. This entire P sub M, which is dependent on xp and yp, must be smooth and locally defined in x and y and M. And Riemannian manifold actually is a pair of this one, M comma G. What is M? This M is simple. It is a differentiable manifold, right? So we know what is differentiable manifold, something on which we can perform calculus. And what is this G all about? This is the Riemannian metric. What is a metric? something which measures. Let us understand for the time this one, right? So it is a pair where M is a differentiable manifold, G is a Riemannian metric. Later on, you will see that this is often just noted as M because the Riemannian manifold, Riemannian metric is implicit in that. Okay. So if we further go, we can just tell that if FV is a real vector space, then on V, this is a visualization, just an abrupt on what is a vector space. Then on V, what we can do, we can choose an inner product. I've just not given V, W or R, just a simple, any kind of an inner product. Once an inner product is chosen, one automatically goes to a norm. This is one V, which defines the length as V squared. And one consequently, we can also define a distant function, which is V minus W. So if M is a differentiable manifold, this one, you now know what is a differentiable manifold, then its tangent spaces, that is T xm, I have just replaced the P with X, it becomes easier for us to understand, are vector spaces. So you see on the right hand side, I have made that red one, T sub xm, these are vector spaces. So consequently, we can see that an inner product on each tangent space has such a coil, which is okay. So let us choose an inner product on each tangent space T sub x and m, and what we get is a Riemannian metric. Okay, inner product, we get it, and this kind of a choice, I'm going to say choosing an inner product on each tangent spaces which is smooth is an Riemannian metric on M. And Riemannian metric actually on M helps us to understand the distance of a function on M. So I hope things are pretty clear till now. So why we are understanding Riemannian metric? Because these spaces and the curvatures are such that we need to get hold of something which will give us a distant function, because it is no more an Euclidean space, so we cannot understand just by doing a square root minus x1 minus y1 plus x2 minus y. We cannot do this simple kind of a function. So we need to get hold of a metric. We need to get hold of some kind of a metric which will give rise to a distance function. Now note that I have been talking about inner product, inner product, inner product. Why? I will just show you. So let us see, in simple words, we can say Riemannian metric is I would say it is a way to measure things. It is a family of smooth varying inner products on the tangent spaces of a smooth manifold. I will come to what do I mean by a family of inner products just now. And it helps us to measure local notions of angle, length, curves, surfaces, area and volume. So you already know that why we called it local, because differential geometry, as we started right at the beginning, it deals with local. Okay. So now just try to understand, I hope you all know, as those who are into physics, you can understand that an inner product is basically a generalization of the dot product, right? Now it is a way of multiplying things together. So we get multiple vectors, we can multiply them, and you know that the result of this multiplication will be a scalar. So now this is the figure, right? The idea is that suppose we need to multiply multiple vectors. This is not only this one vector v. We need multiple vectors. Why? Because on a space-time which is curved, we are moving, multiple objects are moving. So how do we do? So here is a kind of an analogy that these are the multiple vectors which are moving in, right? These are the multiple vectors. So the basic idea is this one. Yes, to equip the tangent space with inner product so that the inner product varies smoothly. And now when this inner products, okay, let me show this animation a little bit later. Let me explain you. So if we equip the tangent space with inner products, what is happening is that because inner product is a generalization of the dot product and we are multiplying vectors together, I will just like to show you again. These are the multiple vectors which are moving in from that tangent space, right? And we need to equip the tangent space with the inner product so that the inner product varies smoothly. Until they are varying smoothly, we won't be able to differentiate it. And until we differentiate them, we won't be able to understand the distance part. So in order to get the tangent space of the inner product vary smoothly, why? Because there are multiple vectors which are moving we need to calculate the vector. So we get this kind of a point, just 2 points arbitrary on the manifold, and then this red line actually is what calculates the distance. Right. So the idea to equip the tangent space T sub xm is why, because we need to get these inner products very smoothly, and it is only then it is possible to define the length, which I have shown in red with 2 yellow dots, of a curved segment on M to define the distance between 2 points. Here is another figure which I have taken from ResearchGate, and you can see this is the tangent vector, right? This is the simple tangent vector, and this is the geodesic. If you remember well, Riemannian manifold actually tells that the shortest distance is the geodesic, and this is actually the geodesic which is moving across. So this is fairly clear, right? So inner product, we need them. It is a family of inner product because I would say a family or multiple vectors are moving. We need to multiply the multiple vectors in order to get the calculation done between 2 points, and only then it is possible to define the length of a curve and to define the distance between 2 points. The right hand side figure shows the tangent vector. What do we mean by geodesic? And the yellow point actually shows the geodesic, and on the top of this pole 1 and pole 2 you can see the tangent planes. Okay, so now the concept is that you see in the definition of Riemannian metric as well as the inner product, we have always seen something which we call constantly smooth and smooth and smooth manifold, all those things, right? So what do we mean actually by smooth? So what is smoothness? I mean to say in mathematics. So we tell them that it is a number of continuous derivatives it has over some domain, right? It is a number of continuous derivatives it has over some domain. Now, we are not going to talk about smoothness particularly in this particular video. We will now take a pause, and this concept of smooth manifold and smooth family of inner products will be explored much in the next video, which will continue with building up the concepts of differential geometry. So in the next video, we are going to talk about what is smoothness, what is a smooth and continuous function, what is a differentiable manifold, into much more details, what is a C-infinity function, and what is diffeomorphism. Right? So I think that's all that covers up the basic starting point of basic concepts of manifold, types of manifold, Riemannian manifold, and what is a Riemannian metric. So the Riemannian metric actually gives rise to the manifold through which we can measure things. So just a quick summary over here. We learned about differential geometry, an overview. We learned about manifold, a brief history. The Mobius part I think is quite interesting. Visualizing a manifold. How do we visualize, get the positive, negative curvatures? What are the different types of manifold we came across? Analyzing a manifold, the local Euclidean spaces, the basic reason why we should learn manifold, Riemannian manifold, and upon that, what is Riemannian metric. So that's all. I think we have covered many part of the video. Do let me know your comment in the comment box. If I have some points to clarify, do subscribe, like, and share my channel. This is Shaunak signing off from Physics for Students, wishing you a great learning and a great weekend ahead. Bye bye and stay safe and happy.
Now, you can be a part of our team. You can send your scientific articles, essays, research papers, lesson plans on a particular subject of science. For further details, please write to us at editor@physicsforstudents.com. Stay safe and happy.